Hi, good evening everybody. My name's Jules. I'm the engineering director at a small company called Tech, where we develop carbon fibre structures for cars. Whilst we've already heard about the wonderful progress with electric taxis for green vehicles, I'm carrying on that environmental theme, but with a bit more width, because it's not just, have a colour. I'm going to talk today. I'm going to talk today really about how we're using lightweighting. So carbon fibre, we all know, is a material that's used to make lightweighting, but I thought I'd just start by explaining why we need to make vehicles lightweight, because it's not just about cars. So anything with an internal combustion engine, it's vital to these days to reduce the CO2 and the particulates. Battery electric vehicles, we've just been hearing about the taxi, want to get as much range as possible out of their vehicle. All that is done by reducing weight. Reducing weight improves efficiency in many, many industries. And it all depends how much each industry will pay, depending on how valuable that is. So in aerospace, where it costs millions of pounds to keep planes up in the air, saving a kilo in weight can be worth between 300 and 700 pounds. So they'll pay for every kilo, 700 pounds more for a component that's 1 kilo lighter on every plane. Bus and coach is nowhere near as that. It depends on the bus or coach. So buses are stopping every few hundred yards. Saving weight is vital, because all the energy that you use to start the bus, you then have to start the bus, you then have to waste when you stop the bus. Automotive, it's a known figure that it's about £5 to £10, because cars are so much cheaper. They can't afford to spend a lot of money on lightweighting. Rail, again, very important on some. I've shown here a picture of a magnet train. It's actually things like underground trains have to be lightweight, because they're stopping and starting all the time. Big pendolinos, doesn't really matter so much, they barely stop. Marine is actually interesting. More and more money spent in marine lightweighting, again it saves diesel. More money spent in marine lightweighting, again it saves diesel, cuts emissions. And the energy world, where lightweight materials are used for their high strength, so getting wind farms out to sea, having windmill blades so huge that the strength of carbon fibre becomes the only way of physically doing that. So there's lots of stuff that's very interesting from a carbon fibre point of view, but I'm going to focus a bit on cars. I'm a car man, so this is the bit I know more about. So emissions have been cut in cars. This is for petrol and diesel cars. And the UK and Europe has been doing very well at reducing its emissions. First of all, when they started reducing emissions, engineers found it very easy to develop better engines. There was a huge change, particularly in diesel engine technology, that brought down CO2 very rapidly, which is my blue line there. However, those changes have been made, and actually development isn't now happening as rapidly. The target, however, carries on getting better, and the target in 2 years' time is 95 grams average. To get to that, they're going to have to take weight out. And why do they need to do that? What happens if they don't meet the target? The car companies get fined in Europe for every gram they exceed the average for their fleet of cars. So that's an awful lot of money for selling cars that don't meet the target. They're not going to do that. They're going to pass those costs on to the customers. So to make their cars cheap, they've got to hit the targets. So, current wisdom, if you want a cheap car, you make it out of steel. If you want a more luxury car, or indeed a taxi, you make it out of aluminium. If you want a very exotic car, make it out of carbon fibre. And the reason for that is because aluminium saves weight over steel, costs a bit more. Carbon fibre saves an awful lot of weight, but costs an awful lot more. We are actually finding our place. with Axontex as a carbon fibre that actually costs the same as aluminium. So we've got the benefit of the even lighter weight for the price of aluminium. The current car technology is more about using aluminium, carbon fibre that costs as much as it does on an aeroplane, but I'll tell you more about that in a second. So, structural carbon fibre was developed in motorsport and in aerospace, which is great because neither of those two industries absolutely give a damn about the cost. They'll just spend what they need to do to get the solution they need. And the way they do that, by cutting out carbon fibre, is very slow, very wasteful, very labour intensive. It requires a machine called an autoclave, which is a very, very expensive vacuum oven. And it's, as I say, it's high wastage. So when you buy carbon fibre, which is a very expensive material, about half of what they buy can end up going in the bin. It's not like you can do with waste carbon fibre, so it's a bit of a waste of money. The people doing this are very highly skilled, which is another way of saying expensive. And they're also finding it very difficult to simulate the way the loads work inside the structure. It is all proving very difficult to automate and speed up. So car companies who are using carbon fibre, I've shown you a picture of McLaren, are basically just spending more and more to get people to build frames quicker and to try and improve the process the best they can. But it is still the same base motorsport process that McLaren actually started back in the 80s. We do it differently. We use a process called braiding. Braiding has been around since, well, for about 200 years. Braiding is the process that made your socks. Probably makes some of our Christmas jumpers as well. But braiding knits fibres together. Shown here in the photograph, knitting glass fibre, which is white, so it's easier to see. This makes tubes of carbon fibre. It's already used quite readily. You can get, if you've got enough money, you Porsche to have carbon fibre wheels. It's used for a lot of prosthetics. A lot of sporting equipment is braided. It's much quicker, it's lower cost because it doesn't waste carbon fibre, and you can make it into many shapes. So it is, and we have developed potential for how this becomes suitable for mass production. And when I'm talking mass production, I'm talking making about 100,000 cars a year in a factory with these processes, as opposed to people like McLaren who are looking at processes to make about 1,000 a year. So, without getting too dull on the detail, the benefits we have using carbon fibre in this different way, this knitted process, is it has lots of strength in different directions. Carbon fibre is normally layers of fibre going in one direction in each layer. So it is actually very good to tune the loads as they go down the fibres, but this has a much more unidirectional approach. It's brilliant for energy absorption, far better than steel or aluminium. So if you're planning to have a crash in a car, it's best to do it in one with an aluminium, with a composite crash system. It is lightweight, it's very low unit cost, and we can make it into virtually any shape. We can make it quickly, we can make it without expensive processes such as the autoclave. So there's a lot of benefits that means this technology is now starting to find its market. And just to put that in graph form, I'm not sure what that graph earlier was in the questions. I've never read it. This is just a common garden graph. But you can see, a bit like the pictures of the cars earlier, the weight of mild steel is going down if you use high-grade steel, but the cost goes up. Aluminium, better weight saving, cost goes up again. Carbon fibre, if it's aerospace, very expensive, but you can get the lightest possible structures. Motorsport, carbon fibre monocoques, yeah, a bit cheaper, but not much. Our process really brings the cost down to within the same value as aluminium. So we've got, I'm sorry, this is dollars, I've got to translate it back to pounds. We've got a process that is saving in terms of a car chassis about $5 a kilo. So go back to what I was saying earlier. It was $5 these days, it's about £5. It's £4 something per kilo saved. So this is now a technology that people are interested in. So aluminium, a bit more expensive, is at times costing £15 a kilo. And the relative mass, you can see that's interesting. So assuming a car body is 100 kilos, a carbon fibre body would be well under half that. So where does that have a benefit? Well, clearly I've explained it has a benefit for saving emissions, it has a benefit for increasing the range on electric cars. But the other benefit it has is that if you are a car company, and we have many around here, then you have to make a car body out of metal, and you need to put in a press plant, you need to put in welding plant, you need to put in paint plant. All that costs about £500 million. If you've already got one, that's good, use it again. If you haven't got one, if you're a new entrant to the market, then you're probably not that keen on spending that kind of money. New entrants using a carbon fibre frame need to spend something like £10 million. They buy 6 composite assemblies from us, I hope, and they bond those together in a simple jig. So that's interesting if there are new entrants to the car market, and there are many new entrants to the car market, particularly those guys who are getting into autonomous vehicles. I put on here, and everybody knows Uber's making their own vehicle, we've heard of Google making their own vehicle, Apple, etc. So these guys are fascinated by their technology, their automated driving. They don't care about designing a car, so they're very happy to go to buy a car frame off a supplier like us. Current OEMs, because they have those big expensive metal plants, can't actually change very quickly. So they're looking to make some parts of their car out of carbon fibre to try and save a bit of weight. If you want to save the most weight, you have to make the biggest change. So I think this repeats the graph I was showing earlier actually. We are going from the process of aerospace, which have very slow cycle times, i.e. how long it takes to make each one, but very low volume, so it doesn't matter. Motorsport, cars, supercars can be quicker, but you make more. I'm talking there at 50,000 vehicles per tool set. We're now looking at factories in China that are making plan to make 200,000 cars a year using this technology. Left that in, but it repeats what I was saying earlier about the cost coming down to that aluminium. There's already a trend that aluminium is replacing steel, and high-strength steels are replacing low-strength steels to get weight down. So the reduction in weight from carbon fibre will carry on beyond that. I'm also throwing up there an example of the Chinese automotive sector. It is going ballistic. At the moment, the number of vehicles in China is going up enormously because the Chinese government are paying grants for EV cars. If you buy an EV car in China and it has a high range, so it will go far enough on one charge of a battery, the Chinese government will give you 100% of the cost of the car. In other words, the Chinese government are giving away cars for free. That's making the number of electric cars, I think it's 2.5 million, growing rapidly every year. So that number of new cars is bringing an awful lot of people into that Chinese market, and they're all looking at this low-cost technology as well as lightweight technology. NIO is an example of a car company that's set up in China but is being developed over here and in the States. They've already declared that by 2030 their cars will be entirely carbon fibre for structures. They started off now with aluminium, they're moving to aluminium and carbon fibre in the next generation, and then by 2030 completely carbon fibre. Huge market potential, as I said earlier. It's not just about cars. Carbon fibre is being used everywhere, and most of the places carbon fibre is being used, then clearly cheap carbon fibre is going to be used even more so. Maybe not the case in planes because they have to have that ultimate performance, but in other areas we can see carbon fibre taking off, even down to trucks. How unromantic is designing a truck, but they've still got to save their weight, so we'll support that. One part of a plane that is actually quite interesting, I've shown it there, is the seats. Planes have hundreds of seats, obviously. And if you can save just half a kilo a seat, then that's a lot of money, because that's still something they value at £700 a kilo. So I'm not going to tell the plane companies that it's actually the same cost as the aluminium. So as long as you don't tell them, we're in for a nice bit of profit there. So not only about car using the car suspension parts, etc. Very high volume, very easy to do in these new materials. And again, a nice graph to show where we are currently with UK capacity. I should grow that arrow a bit now. McLaren have actually moved their body plant back to the UK, but it's still pretty expensive per part. This is our cost model showing how the price comes down with volume. So having automation and putting volume into the same production factory brings the cost down. And there's a very interesting, well, I find it interesting, I would, bit going on here that if you then start making this volume, our 200,000 vehicle factory in China is going to use 5 times more carbon fibre that is made in China anyhow. If we get up to making 1 million frames a year, we're going to use more carbon fibre than is made in the world. That's not a problem. That just means more people will be making more carbon fibre. The more people make more carbon fibre, the cheaper it will get. So these costs are assuming today's market price. We know full well that as volume takes off, this market price will come crashing down. And there's another thing which, if you're not working at industry yet, you want to learn about, that everybody does OPEX, which is everything you do, you try and do it next year better, cheaper, etc. So that also brings cost down the top line. And that's me wrapped up. So a few slides of the stuff we get up to with Exentex. Any questions? Yes.
I actually have 2 questions.
Yeah.
So first, because carbon fiber panel actually reduce weight a lot, will that kind of affect the dynamic side of the style of the car? Because you need to have certain weight to stand the wind and all of these effects.
No, not at all. We envisage structures. You can see some of our structures. The 2 at the top are a small EV and an SUV. Both those, you see the carbon fibre we make is the understructure.
Yeah.
So onto that we will bond what I call we call the A-surface panel. So the actual style panel will go over that.
Yeah.
That will provide the kind of visual looks of the car. But the benefit of having your structure separate from your A-surface is it's very easy to change your style.
Yeah.
It's very easy as well for us to design an SUV that can be bought by 4 different customers, that they then stick 4 different styles on the outside. So you can use the same underbody on many cars. I also think because carbon fibre lives so much longer, we talk about recyclability. Your car's out there 10, 15 years old, off to the scrapyard, it gets melted down, great. How about you don't ever need to replace your carbon fibre structure, but after 10 years you buy it a new look exterior. You just have a new exterior put on it, because the structure will go 30, 40, 50 years, which currently you can't do. So sorry. And your other point?
Oh, the other one is, say if you have a steel panel,
Yeah.
and there is a cut on it, it wouldn't largely affect the strength of the other part. But as the carbon fiber is grading, if there is a cut there.
Good question, and you reminded me that Calvin brought some bits in, which I left lying around. So I'm going to pass these up to you, or it'll come up to you. Huh? So I'll just explain. I don't know if you can all see, that has been bent in a test against a very sharp edge. It is broken from here right down there. 95% of its width is broken. Now, I was explaining earlier about motorsport planes where they have layers of carbon fibre. You can get a failure in carbon fibre between the layers and you can never see it. In fact, if you just go onto the internet and look for broken carbon fibre bike, you'll see this happens, because people hit a pothole on the bike and it virtually collapses under them. This has been failed, as I say, through to 95% with a 15-ton load on it. And that is still got 60% in its overall strength. So it's very obvious it's broken. So in terms of steel, if you bent it, you can see it's bent and you've lost some load. This braided carbon fibre behaves very much like steel. So can I ask you to, well, have a look yourself and then pass it back. I've got another bit of structure, and Calvin will be in trouble if he doesn't get these back to work on Monday, so have a look at that. So that, the round piece is the same strength as a steel bar, 8 times its weight. Calvin, you've seen it before. Okay? Does that answer your question?
Yeah, I guess the answer is it wouldn't affect the strength.
No, it wouldn't. Well, it does slightly, but in car terms, if that was your suspension and you hit someone, I mean, you'd still be safe driving. You'd think, oh, this isn't right, go to a garage and they would see a failure and replace the part, rather than you have an instant failure and be stranded or worse. Any other questions? Now I've got bits of carbon fibre flying around the lecture theatre. I'm glad I didn't remember those at the beginning. If you want to try and break that beam further, feel free. No, just try and break it right back. It took 15 tons to break it. It'll take about 10 tons to move it further.
That's when I smashed my head against and I get stuck in work. So this spiked my head. It was like, well, yours. Fine.
We didn't hit you over the head with it. Oh, you hit you over the head with it. I don't know. Okay, any more questions? I think I'm handing back to the quiz.